Lecture 3. I'll try to keep my hand out of the way. I can hear my son singing in the background. Who, for some reason, wants to go to Clemson. Boo. Alright. So now let's say that we've got a something we want to find the inverse Laplace transform of. And this is the simple case. Normally I've got a polynomial on the top and the bottom. In this case we're going to just say the top is P of S. And the bottom, let's say I can factor it down into its poles, or the roots of this polynomial, S plus S1. So we've got a pole at minus S1, or a root at minus S1, S plus S2, dot, 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 S plus S of N. Right? Sometimes it's tough to factor it, to get it into this. A lot of times that's where you end up having to use an advanced calculator to find the roots of this equation. So in this case, where we know that the S1, S2, and Sn are all real and they're non-repeated, what I want to do is I want to break this thing up into separate pieces, because then it's easy to find the inverse Laplace transform of the small pieces. So can I do this? Can I figure out what A is, or what B is, or what M is? If I can do that, if I can figure out what these top pieces in, then it's fairly straightforward to find the inverse Laplace transform of just this piece, or just this piece. The way you do it is, this is called partial fraction expansion. I don't know if you learned this, Jared. You may have learned this in high school, some of this. Where A is going to be defined, what I'm going to do is, if I'm trying to find A, I'm going to take this whole piece and multiply it by this component. So this part will drop out. So it's going to be S plus S1 times this whole thing, P of S over S plus S1, S plus S2, dot, 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 S plus S of N. And you're going to evaluate it. So this and that are going to cancel out. And you're going to evaluate it, though, at this root, at S equals minus S of 1. So an example is easier to follow always. So let's do an example. Let's say that I've got an example of x of S equals 5s plus 3 in the numerator, and I was able to factor the denominator down to s plus 1, s plus 2, s plus 3, and I said, hey, I want that to be in this form. Something times something over s plus 1, call it A, B over s plus 2, and C over s plus 3. The question is, what does A equal? So I go back here. A is going to equal, or take this, s plus 1, times this whole thing, right? 5s plus 3 over s plus 1, s plus 2, s plus 3, and I want to evaluate it at s equals negative 1. So that and that are going to cancel, and this is going to be 5 times negative 1, which is negative 5, plus 3, and then I plug in negative 1 to here. Negative 1 plus 2 is 1, Negative 1 plus 3 is 2. So I've got negative 2 over 2 equals negative 1. Okay? Similarly, B is, got the s plus 2 term, so I get rid of that piece and I evaluate the rest of it at s equals minus 2. So I've got 5s plus 3 over s plus 1, s plus 3, evaluated at s equals minus 2, and that's going to be minus 2 times 5 is negative 10, plus 3 over negative 1, positive 1, negative 7 over negative 1 equals 7. Similarly, I'll let you figure it out, but C turns out to be minus 6. So do that one and make sure you get the same answer. So we'll stop this now to keep the limit short, and we'll finish this off in the next lecture.